Good morning, everybody.
Good morning.
It's time to go wee! Right? I mean, that's why people go on roller coasters, right?
Yeah.
The wee factor? Or is it just people love throwing up?
Maybe.
Maybe? Part of the wee factor? I don't know. I do like roller coasters. As I've gotten older, I like them less because they just like hurt when you're done, right? Between my neck and my back. But if somebody assures me that it's I don't want to call it a gentle roller coaster. I don't mind the accelerations. It's the sudden, like back and forth or sudden stops and that kind of stuff, right? The jerkiness of a roller coaster. So I stay away now from roller coasters that are like made out of wood, like those kind of old-timey roller coasters. More modern ones, right? They're pretty fun. I have no problems with being upside down or anything like that. So what we're going to do is we're going to do the roller coaster. And this is applications of everything we've been learning about, like free body diagrams, Newton's laws, this process of analysis, these steps that we take in order to just figure out what's going on in the world. So let's see. We need a circle. All right, and what we're going to do, we're not going to do every point on the circle. We're going to take a look at a couple of places, and one of those places is going to be at the bottom of the circle. And then the other place we're going to do this is the top of the circle. So this is like a loop-de-loop in a roller coaster as pictured. However, if you look pretty closely, is that loop-de-loop a circle? No, we'll talk about that at the end. There's tricks going on there. Okay, so what we're going to do is we're going to analyze the forces on a rider at the top and bottom of the loop. And it actually doesn't matter if we're talking about the person riding the roller coaster or the roller coaster car. We don't need to get into the nitty-gritty details of what's going on with their seat and the harness or any of that kind of stuff. That's all there for safety. We're talking about the forces that are acting on objects when they're at the bottom or top of a roller coaster track. So let's tackle the bottom first. Okay, and again, we do have to think about like objects. So just as a simplification, let's consider like the person and the roller coaster car and all of those systems. That's just kind of one object. Okay? If the roller coaster feels a force, then the person in the car is going to feel a force. You're connected to it. Okay? So let's just think about the roller coaster itself, the car on the roller coaster. What objects are pushing or pulling on the car at the bottom of the roller coaster? So the earth, and that's going to cause the gravitational weight, isn't it? So that one points in or down. Okay, what else? Another object. The track, right? Okay, and so what direction is the track pushing on the cart when it's at the bottom? Up, right? Because inward, well, not always inward, maybe. Okay. There is a normal force. And why is there a normal force? What two objects are in contact? The track and the car, right? Okay. Are there any other objects pushing or pulling on the roller coaster? Oh, okay. Well, did physics land? We're trying to do this as like simplistic as possible, right? So no air friction, no rolling friction. We're going to strip all the friction out. Where do roller coasters get their like speed from? Their oomph? Are roller coasters like propelled along at every moment on the track? Does like the track like push them forward? No. Where do roller coasters get all their oomph from? Right? They either take you up high, right? Because that's terrifying in and of itself, right? They really don't need to make it go tick, 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 tick like that, right? Okay, right? But it just leads to the, oh, I'm going to die, right? Okay? And then, right? Or more modern roller coasters. So my family's really annoying. My sisters in particular. They went to Disney World this year. this summer, and they couldn't say anything better than Tron ride. That's like all they talked about, right? And they know I love Tron and everything, but apparently in that ride, the way you get going on it is this massive acceleration, electromagnetic acceleration at the beginning, okay? They take you from like 0 to 60 in like 2.5 seconds or something. And so in that case, they are using magnets and electricity to give that initial propulsion, and then after that, little boosts here and there, but mostly ups and downs. Anyway, so there's no other object. Long way of saying there's no other objects acting, pushing or pulling on this cart, which is kind of interesting because now we've got to figure out what the heck's going on and what we're doing here. We need a coordinate system. Some way of talking about positive and negative. Well, I guess. I don't want to go make it that hard. To be able to set a coordinate system, first of all, is this a static case? Are the people in this roller coaster loop-de-loop being accelerated? Yes or no?
Is their velocity changing?
Their velocity is not changing. Then the answer is yes, because what are they doing in a circle? Direction is changing constantly, right? It's such a trick, right? Remember the last quiz about how many accelerators there are in a car? If something's going in a circle, it's being accelerated. And which way is that acceleration pointed? Inwards. So we're going to assume that acceleration is centripetal and inwards because it's going in a circle, which means that I want to make positive y be up. Okay? Do I need to define positive x? Are there any horizontal forces? There aren't any, so you could do it if you want, but it's not gonna help us. Okay, so at the bottom, right? Newton's second law. Mass times acceleration equals sum of the forces. There's only a y direction, so it's ma. You can say y if you want. Equals, and then how many forces are there in the y direction? 3, 2. 1, 2. Yeah, don't look at the acceleration. So that's normal and the weight, mg. Which way is the normal force, positive or negative? And mg? There we go. Okay, so we wrote down the equation, Newton's second law, for the riders at the bottom. Put a pin in that. We're going to come back to it because we want to do a compare and contrast. The goal of this example is to explain why people go whee on a roller coaster. That's our goal. And we're going to figure it out, believe it or not, with these equations. And hopefully not ruin roller coasters for the rest of your life. Okay, which way is gravity pointing at the top? Still down. Good. Okay. Still down. Which way is the normal force at the top? Down. This is a loop-de-loop, right? They're upside down, and the surface of contact is up there, and therefore the track can only push down on them. Which way is the acceleration? Towards the center of the circle, which also happens to be down. So which way are we going to make positive? Down. Everything's down from here on out. You guys have dads and have exposed to dad jokes, haven't you? Jeez. All right. So at the top, M-A-Y equals, all right. How many forces? 2, N, and mg. And they're both positive this time. Oh, that's different, right? Okay. So here we have an equation in blue for the top, and then we have an equation in red for the bottom. And there's something different about them. And it's that minus sign, right? That's sitting there. Application of Newton's second law has given us two slightly different equations that lead to a pretty big difference. So what do I mean by that? I'm going to first, let's take care of these accelerations. It doesn't matter which one we're talking about. Centripetal accelerations the magnitude of them can be found if we know how fast something is going, its speed in meters per second in the circle, and the radius of our circle. So we'll assume that we can kind of, maybe we're given those things. We'll do something with them at the end. But basically, I can go ahead and substitute the v squared over r in for the acceleration in both of these equations. And really, that kind of makes the mv squares over r's. I mean, is the mass changing just because we're at the top or bottom? No. Is the velocity changing just because we're at the top or bottom? No, we're going to keep it the same speed. Is the radius of the loop-de-loop changing just because we're at the top or the bottom? No. So that's something that's the same, right? In whether we're at the top or the bottom. Does the weight of the car change just because we're at the top or the bottom? No. So what's the only thing that's different? Yes, where you're at, but these equations don't say anything about where you're at. What's the only thing that can be different? The normal force. Watch. If I solve the equation at the top for the normal force, move the mg over to the other side, reverse all the terms, then I get mv squared over r minus mg. There's the normal force at the top, right? At the bottom, if I solve for the normal force, the negative mg moves over, becomes positive, and I get mv squared over r plus mg. What's the normal force? I didn't ask a trick question. What is it? Real simple. What's the force? Push or a pull. The normal force happens because
The track's pushing.
two objects come into contact with each other, right? The normal force, the force of contact between the roller coaster and the track, is different at the top and the bottom. The reason it's different is because gravity stays the same direction, but the orientation of the track is changing. So what does this mean for a rider on the roller coaster? What normal force are they going to feel at the bottom compared to the top? mv squared over r is the same whether at the top or the bottom. The weight is the same whether we're at the top or the bottom. So which normal force is going to feel bigger? This n, the red one, is bigger than the blue one. And why is it bigger? Plus. So a rider on a roller coaster feels more normal force at the bottom of the loop than at the top. Park that for a second. Let's talk about the scale in your bathroom. Okay? When you go to step on the scale in your bathroom, what is the only thing that your scale can tell you? Think about the song. No. The scale cannot tell you how much the earth is pulling on you. What is the only thing the scale can tell you? How much you are pushing on the scale, and the scale is pushing back on you. Because it's you and the scale, right? Now, we make a mental leap there to say, well, that's my weight. That's what the earth is pulling on me. And that's true if your acceleration is 0. With you just standing on the scale in the static case, assuming that your restroom is not accelerating, which might depend on how good a time you had last night. then what you are pushing on the scale and the scale is pushing on you happens to be the same as what the earth is pulling on you and you are pulling on the earth. However, if you step into an elevator with your bathroom scale and you stand on it and you push the button and the elevator starts going up, what do you suddenly feel? All those Snickers bars just caught up with you, right? You feel heavier, and you can actually read that on the scale. The scale will say that you gained weight. Did you gain weight? No. What happened? To accelerate you upwards and get you to the next floor, what did the elevator have to do? It pushed on you upwards, right? But the scale doesn't really know that. All the scale knows is like, hey man, you're pushing on me more, so I'm good. Right? This is an effect that we physicists call apparent weight. People talk about their weight, but what they are really talking about is the normal force. The apparent weight a person feels is the amount of normal force that's acting on them. People don't directly measure the force of gravity acting on them. The reason that you feel like you have weight is because the floor is pushing back on you. If you jump in a pool, now what do you feel like your weight is? Less. Almost zero. Float there. Did gravity shut off? No, right? But we took away, in effect, the concentrated normal force of the floor and spread that normal force all over your body, right? With the water molecules. So apparent weight is this idea we have in our brains of how much we weigh, but we can change the apparent weight by just accelerating a person. You feel pushed back in the car. You feel pushed up by the elevator. When the elevator gets to the floor and comes to a stop, what do you feel? Lighter. Again, did gravity change? No, the amount that the floor is pushing on you changed, and people will swear, oh, I lost some weight. Fastest weight loss program. Anyway, let's go to the elevator. Right? So, or go to the moon, one of the two. So, what's going on with the roller coaster? I just taught you that people's what they think of as their weight is really the normal force acting on them. So a roller coaster rider will feel what at the bottom? Heavier. They'll feel heavier because the track and the car and everything's pushing up on them more. And then when they get to the top, what do they feel? Lighter. And that's where the we comes from. The feeling of ooh and ha, changing all the way around that circle, right? And then, of course, being inverted and feeling like you're going to throw up. And people do a lot of stuff called fun that it leads to throwing up. I don't know. All right, so let's extend this. So we found out where the excitement comes from, but let's extend this to: is there a case, either at the top or the bottom, where we could get rid of the normal force completely? Can the bottom red equation go to zero? No, it's adding two things together. It can't get to zero that way, right? What was the top equation? Yeah, there's some subtraction there, right? So we could do something where the normal force could become effectively zero. And what would a person then experience if the normal force goes to zero? Weightlessness. They would feel no more normal force, which is like equivalent of being dropped off of a cliff. Okay? Again, that sensation of going from, oh, I'm really heavy to, oh, I'm not being held up by anything, right? So what speed does that happen at? If the normal force goes to zero, then mv squared over r equals mg. I just put zero in that equation and then move the mg over so it becomes positive, right? The masses cancel. So the mass of the rider has no effect on what I'm about to say. You must be this tall to ride this ride. Why?
Mass doesn't matter.
Mass doesn't matter, but height does. Why does height matter?
So you don't fly out.
So that the safety systems can hold on to the person, right? Okay. However, mass doesn't matter. And we solve for v, we get the square root of r times g. Okay. That right there, okay, is the speed that the roller coaster has to go at in order for a rider to feel weightless at the top. If there is no system in place to keep the car on the track, the car would fall off at this point because the normal force would go to zero. You're no longer in contact with anything, right? But that's why they put wheels on the bottom and top of the track, right? So that the car always stays attached to it regardless of the speed that it goes through. The reason the picture's roller coaster is like a teardrop shape instead of a perfect circle, this moment of weightlessness at the top only happens at the very top for a perfect circle. For a teardrop shape like this one, you can actually extend the zone because the radius of the circle is constantly changing in this teardrop shape. So you can actually kind of, instead of it just being an instantaneous moment, right, at the top, it can actually be this like extended moment at the top. And again, the wee factor goes up or whatever, right, for that sort of situation. But you can explain why people go wee on roller coasters. And I'm not talking about doing a number one. What the heck is going on here? I mean, we're used to seeing roads kind of do this, right? This banked turn, right? I went and looked for pictures on the internet, give me pictures of a banked turn. And this is one of them that popped up, and I couldn't help it. I had to put it in, right? If public transportation were like this, I'm there, right? Like that looks fun, right? Now, can the bus do that if it were like parked like that? No, right? This bus has to be moving, right? To be able to pull off a trick like that. This picture came from the Mercedes-Benz test track in Germany where they test all of their vehicles, and apparently buses have to go through the same test. But they're testing, and they move them around at speed, and they can stay in these turns, believe it or not, even if there's no friction. The reason that turns are banked and have so if you go up into the mountains and you start driving around and they kind of bank, sometimes very severely, the turns, is to make sure that the car can stay in the turn even if the friction goes away. And so let's do that problem, okay, where we do the banked turn. I apparently did not include the slide that took the bus off. So let's, can't use that one. Let's just grab a piece of paper here. All right. Good. All right. So, banked turn. No friction. What I'm going to draw is a cutaway view of the banked turn. This gets slightly confusing because, by golly, Mr. Balogh, this looks exactly like sliding down a ramp, doesn't it? Okay. The problem here is, though, is I had to do a cutaway view. It's like I take this picture and I just sort of slice it, right? And I'm looking at it edge on. And so in this picture right here, the car is coming at us out of the screen. It's driving around this banked turn, and I've done a cutaway view. So the car's coming at us out of the screen, and we're going to try and analyze just what the heck is going on. We're going to assume it's a very icy road, and we're going to do the same analysis we've always done. What objects are pulling? Well, the earth pulls. And the normal force, right, from the surface of contact between the road and the car are right there, like the car's tires are right here. Again, it's a front view. Those are the headlights coming at us, okay? Now, are there any other objects / forces that are acting on the car?
You said there's no friction?
There's no friction.
No air?
No air, no road friction. This is a car on an icy turn. It's going in a circle, right? But the circular path is like this horizontal path, isn't it? Okay? It's not like the circular path is tilted, like right? The car isn't, right? It's going around in a horizontal circle, right? And so we know the direction of the acceleration for this car. What direction is the acceleration? Towards the center of the turn. That should have been red. Towards the center of the turn, right? And our rule of thumb tells us to do what? Always put a positive direction for an axis in which direction? Towards the acceleration. So I'm actually going to call positive x to the right. And I'm going to call positive y up. We want to keep this so that when we write our Newton's second law equation in the x and y directions, I didn't do it that way before, in the x direction and the y direction, I want to make sure that I can write max equals and may equals and have one of these turn into 0. In this problem, which one of these is going to turn into 0? Not x. It's y. Our acceleration is only in x. So that's non-zero. But did we put any acceleration along the y-axis? No. So we're going to let that one go to 0. So that's 0 equals. Okay. We need to find components, don't we? Which force do we have to find the components of? This time it's the normal force. It's not mg. When we did like the hill problem where someone was sliding down the hill, we had to break up mg because it was the one that wasn't lying in our coordinate system. All the other forces were nice. But in this case, our coordinate system is perfectly up and down, and it's the normal force which is behaving badly for our coordinate system. So if I just kind of come in here and I drop a little imaginary coordinate system, aligned up with my x and y's, right? I can see now that my normal force needs to get broken up. And my normal force needs to get broken up into nx and ny directions. If we know the bank angle, I don't really want to bore you with any of the trigonometry here, okay? But it turns out that that angle of the hill is the angle right in here. My drawing is getting very sloppy, okay? So, after yesterday's lab, and knowing what you know about touching, not touching, how are we going to write down ny? Sine or cosine? It's cosine. And why is it cosine of the angle? It's touching that angle. Again, I skipped over the geometry to get to that, but you can trust me on that. nx, sine or cosine? Sine, because it's not touching that angle. Okay, and away we go. In the x direction, how many forces are there? 1. And it's n sine theta, because it's nx. And in the y direction, how many forces are there? 2. N cosine theta and mg, and n cosine points up and mg points down. Okay, and there's a positive sign over here on my x direction one. Okay, so what can we figure out now? It doesn't feel like we can figure out much. We don't know what the normal force, so let's just say, for sake of argument, that we know the mass of the car, we know what planet we're on, and we know the angle at which this turn is banked. Okay? And then, because it's going in a circle, let's say we know the radius of the turn, and we also know how fast the car is going. Or let's not say we know how fast. Let's find out how fast cars can go and still be safe in a banked turn with no friction. That's what we're after. So now we got to put some pieces together. N over here, n cosine theta is going to be equal to mg. So n is going to be equal to mg divided by cosine theta. And now I can go ahead and chuck that into here. Oh my gosh, this is going to get horrible. MA equals the normal force, mg divided by, this isn't going to be so bad. Okay, wait, I was worried. What's sine divided by cosine? It's tangent, isn't it? Mg tangent. So that was nice. I ended up, not only did I get rid of a denominator in a fraction, I hate fractions, but I was going to say I got tangent, but I don't like tangent. Tangent's dumb. Okay. Can I clean up anything else here? Doesn't matter if this is a bus or a car or a bicycle or a dog? No. Okay. That's kind of interesting. And then this acceleration. It's a centripetal acceleration, isn't it? This car is going around a turn. Okay? So it's pointing towards the center. And that centripetal acceleration is equal to g tangent theta, which means that v squared over r is equal to g tangent theta, which means that the speed at which a car can safely negotiate a turn with no friction isn't zero. For a given radius of turn and a planet that you're on, in most cases Earth, 9.8, and an angle that isn't zero, the tangent will have a non-zero value. This is a non-zero value if you put numbers in other than zero, right? So that means, based on the radius of the turn and how steeply banked it is, there is a safe speed it can take. And if the turn is banked at 90 degrees, tangent of 90 is what?
1.
No. Try again. If you ask your calculator, it's going to freak out.
Oh.
What is it?
Domain error.
Domain error. It's infinite. Which means that the speed that you can go and safely stay on a vertical wall as you're going around is infinite, right? Okay. Now there are minimum speeds. You can drop off that wall. One of my students from India once shared a video with me, and I wish I had it, of circus performers in India driving cars in a well. They were almost vertical sides, and they were driving around on the inside. They would start at the bottom and they would go really fast, and then they'd come up onto the walls and they'd stay on the walls for their race. Nuts. What happens if the angle is 0? What's the tangent of 0?
0.
It's 0. So how fast can you go on a flat turn with no friction? You can't. You can't stay in the turn. There must be friction for you to stay in the turn. So if you hit a patch of black ice on a flat turn, you're ending up in the ditch. Banked turns, even if you hit patches of black ice, in theory, there is a speed that if you exceed, you'll fly off, but if you are at that speed or under, you will stay on the road. This is why we bank our turns. That, and it does help to get the water off. All right, let's keep applying all of our circles and do some rocket science. Ladies and gentlemen, this is rocket science. I don't know why they say rocket science is so hard when they're trying to say something is hard. It's not like it's rocket science or something. You should put in, I don't know, organic chemistry into that line. Because that's hard. Okay. Different structure, different folks. Well, okay. So what's an orbit? Orbits don't have to be circular. They can be elliptical. They can be hyperbolic, actually. That's kind of a weird case. But anyway, what's an orbit? What kind of things orbit? Planets orbit what? Suns, stars. What else orbits? Moons orbit planets. International space stations orbit. Satellites orbit. Do all these things have in common? Well, they all have different masses.
Big.
What?
Big.
They are going around something big. Okay. So we'll just limit all of our ideas right now to planet Earth. Okay, the things that in orbit around planet Earth. Just make it simpler. What do all things in orbit have in common around planet Earth? They're getting pulled. If you have a tennis ball and a string, you can lecture on any physics subject, okay? So here my tennis ball is a satellite going around the Earth, right? Now, in the case of my tennis ball here, it's a string. But in the case of the Earth and the International Space Station, what is the string? It's gravity, right? So what's an orbit? Well, a gravitational pull, that's a force. How many forces are acting on the International Space Station as it orbits the Earth? Assuming a perfect, vacuum in space, and we won't say that, because the International Space Station is actually in part of the Earth's atmosphere, but it's very thin. Anyway, assuming no friction. And assuming it's just the Earth and the International Space Station, because there's the moon and there's the sun and there's all of the satellites. Okay, right? Just talking about the International Space Station and the Earth. How many forces are acting on the International Space Station? One? No other objects pushing or pulling on the International Space Station except the Earth. Okay, so if gravity is the only force acting on the International Space Station, by definition, what is it doing? Gravity is the only force acting on it. It's in free fall. What's an orbit? It's falling towards the Earth, but never getting any closer. This is the part where I drop the mic and I walk out. I mean, that's almost the same way as defining flying as throwing yourself at the ground and missing, right? It's like, that's a true statement, but my brain can't do it. But that's what's happening when objects are put into orbit and maintain their orbits. They are being influenced by gravity alone. However, somehow they're not getting any closer to the surface of the Earth. How is that possible? What the heck is going on? Flat earthers don't like what I'm about to say. Because what am I about to say? If you can get going fast enough sideways, then in the time it takes you to fall 1 meter vertically, the Earth will have curved away by that 1 meter. And you can forever be in free fall and not get any closer. When rockets launch, arguably, up is an important direction, but really not for the reasons that you think. Space is only a 1 hour drive in your car if you could drive at 60 miles an hour straight up. It's 60 miles away that way. That's it. Space is pretty darn close, okay? What we need rockets to do isn't really go up. We need to get them to go up to get out of the atmosphere so there's no friction. But what we really need to get them doing is moving sideways. You need to get going sideways fast enough in order to fall and not get any closer to the surface of the earth. So let me show you an animation from some of my favorite old videos. Let's see. Go away. That's not the one we want. We want, what chapter are we in? 4. 5? 4. 5. Come back here. Right there. And here's our little...
Newton's argument was to imagine
Okay.
someone
I'll
casting a
narrate
projectile
because
horizontally.
the audio doesn't work.
Firing
We got a little
cannon, for
soldier
example,
loading a cannon,
from
right?
somewhere high
Okay.
above the Earth's surface.
And if you don't put enough gunpowder in the cannon,
From Galileo's discovery, Newton already
doesn't go
knew
very far,
that
right?
a body dropped from
gravity
16
takes
feet
over.
above the Earth's
So if you
surface
load up with, say,
reaches
more
the ground
powder,
in 1
right?
second.
Okay, and you fire, you're doing a good job there, guy.
The distance a
So
cannonball
more
travels
oomph, right, gets
depends on
more
its
like
velocity.
horizontal
If
range,
the projectile
right?
leaves
Assuming
the
for a
barrel at 30 feet per
horizontal
second,
launch, right?
it travels 30 feet
And here we go,
before
right?
it
We're
hits the
gonna,
ground.
ooh, double
1
charge.
second
Okay,
later.
all right. Zoom out. We
But
launch.
Newton realized
Boom. Okay.
that if
Oh,
the projectile
ooh.
were fired fast
But what happens if we load
it
up
would
with
take more
enough
than 1 second to reach the
oomph?
ground. The Earth
so
would
that
curve
when you
away
fire,
before the cannonball reached it.
The cannonball can move sideways
In fact,
far
you
enough
can imagine a cannonball moving so fast
so that the Earth
it would
can
never
curve
strike
away
the ground.
beneath it.
It would just keep falling
So
forever.
Newton figured
while the
this
Earth
out
forever curved
long,
away beneath
300 years before
In
we
other
would go to
words,
the moon.
it would
right?
be in orbit.
Knew how to put things in orbit, all that kind of, this guy better duck. If you think about it. Because, yeah, duck, duck. Oh, they
Zero G,
Okay.
or weightlessness,
And then they're gonna
isn't
show
really
some.
the absence of gravity.
They're going to show some
Astronauts orbit the
people
moon.
floating around on the International Space Station. Okay, so, or actually that was the lunar module around the moon. So that's in orbit. Shoot something fast enough sideways, okay, so that it never gets any, oh, that's right, I got to show the other one. But I got to pause the recording because YouTube will do a copyright strike. And what does that have to do with people like this guy that really know how to rock a collar? I mean, look at that thing, man. You think neckties and bow ties are a problem? Wow. One of these days, I'm gonna come to class wearing the old the graduation robes that everybody wore. You understand that those are what teachers and students used to wear at school back in the 1600s and stuff. Yeah. All right. Why are we talking about old dead guys and Kepler's laws? So before Newton, Johannes Kepler developed 3 statements about orbits, about planetary mechanics, orbital mechanics. So this is pre-Newton. So Kepler is not working with the benefit of an understanding truly of what force is, what energy, none of these things, right? All Kepler had was tons and tons of data about planetary orbits. And if you want a really fun story, you should go check this out because this is like a soap opera. It involves the death of a king and a theft and the rightful ownership of something and fleeing the country. Oh my gosh, it's great. But we don't have time. This is not a history class. All right, so what are Kepler's laws? 2 of them are conceptual statements and the third one has math in it. Number 1, what did Kepler discover? By the way, these are so important that Newton used these laws to prove that his laws worked. That's how foundational this was. Number 1, Kepler discovered that the planets' orbits are elliptical. So prior to Kepler, there was this understanding that planetary orbits were circular because circles were perfect and God's creation could only be perfect, and so on and so forth. And so everybody just assumed that the orbits were circular. If you're trying to get from the Earth to Mars, and you don't want to miss, because missing is bad. If you miss Mars on your way to Mars, coming home takes a really long time. So you don't want to miss. So it's actually pretty critical to understand that the planetary orbits aren't exact perfect circles. Having said all that, we will assume that because the math of circles is much easier to deal with, right? But bottom line, all planets' orbits are elliptical. If we could stand outside of our own solar system and kind of look down on it from above with our eyeballs, we would think that all the planets' orbits were circles. Like they look really close to circles, just like from our, using our eyes. It's only with very careful data that you can find that, in fact, they're very slightly non-circular, which is really important for knowing where it's going to be at the right time, in the right place. Okay, so that was the first thing that Kepler discovered. Number 2. He discovered that the speed at which planets orbit changes. They speed up and slow down depending on where they are in their orbits. And the best way to talk about this one is really to draw a picture. It's sometimes called the equal area and equal times law, which is complicated and well, not complicated. It's cumbersome, unwieldy. We call it Kepler's second law. But this is what it is. And I'm going to exaggerate my ellipse now. I know planets don't do this, but this is top-down view. And let's say this is the sun, and this is the orbit of Earth around the sun. Okay? So the Earth is going around the sun in this highly elliptical orbit, which it isn't. The Earth's orbit is very nearly circular, almost. Okay, what Kepler discovered is that, let's say the Earth moves from one point to another, and let's say it's going around this way, okay? So the Earth starts, like we measure like its position here, and then a month or two later, we measure it here, okay? And then we draw like a pizza slice. There's an arc, and we draw from the sun, which, by the way, the sun is always at the focus. Well, an ellipse has two focuses, right? Two foci. And so the sun is always at one of them. So if you draw and you make a pizza slice, and you find the area of this pizza slice, Kepler wasn't thinking in terms of pizza, because pizza didn't exist at the time. And then you take another 2 points somewhere else in the orbit, and you make a pizza slice that has exactly the same area. Then the amount of time it takes the Earth to move along its arc is equal. In other words, equal areas in equal times. Now, in order for this to be true, like, where is the Earth moving the greatest distance in its orbit? Like actual distance traveled. Is it the points close to or further away from the sun? Close to is where it's moving the most, right? So this arc is longer close to the sun versus the arc that's furthest away, right? So if the Earth has to move a greater distance in the same amount of time, what do we know about how fast it's going? It's going faster there. So another way to talk about Kepler's second law is that planetary, like orbital speed is fastest when the object is closest to the thing that it's orbiting. You get further away, orbital speed goes down. We haven't learned about conservation of energy yet, but Kepler has discovered conservation of energy about 75 years before anybody would even think of the word energy. Okay? Things move fastest when they fall close to the things that are pulling on them. So that's Kepler's second law, equal areas and equal times. And then the third law is the one where we can finally get some math in, okay? And maybe finally, maybe not finally, but horrifyingly, we can get some mass in. Because it is horrible, and I have to look up how your book does it. It says that the period that a planet the time it takes for a planet to complete one orbit is equal to 2 times pi times the radius of that planet's orbit. That's defined as center of mass to center of mass. So like if we're doing Earth's orbit around the sun, that's center of sun to center of Earth, okay, that distance, which we often just say is the distance from the Earth to the sun, divided by the square root of big G times big M, and that radius is to the 3/2 power. Please don't shoot me. It is not my fault. It's Kepler's fault. Actually, it's the universe's fault, okay? This looks like a big nasty. What does a 3/2 power mean? You raise anything to the half, what does that mean? There's a square root involved, right? And then what's the 3 power mean? Cubit, right? You're cubing it instead of squaring it, okay? Your calculator knows how to do this, right? So, but what Kepler has discovered is that the orbital period of planets isn't some nice multiple, right? It's this horrible, awful multiple of r to the 3/2. In other words, we usually define the 1 year, right, the time that it takes Earth to go around the sun. We call the distance in astronomical units. This is what astronomers do. They call that 1 AU. 1 astronomical unit is the distance, the average distance of the Earth's orbit. And it would be nice if, say, Mars, which is almost 2 astronomical units, almost twice as far from the sun as Earth is. It would be nice if a Martian year were twice as long, but it's not, okay? It's r to the 3/2 power long, right? Okay, double the distance, you got to throw that in there and cube it and square root it. It's terrible, right? But it's important, again, for knowing how to get somewhere and be there at the right time to meet the object. Doing orbital mechanics and getting things to go places in our solar system is a tricky job. It's kind of like having to, I'll put it this way. This is how the NASA engineers described getting the Curiosity rover onto the surface of Mars, which, by the way, this week they released scientific data that showed that they found a biosignature, or a very likely biosignature in a Martian rock. Meaning that they've, other than just holding it in our hand and going, yeah, there's life here, we pretty much discovered signal of life on Mars, just in case you weren't aware. That's been reviewed, peer-reviewed, all that kind of stuff, really good evidence. We just need to get the rock back to confirm. Okay, so, which is several billions of dollars more to do that. If you want to get to Mars, if you want to get the Curiosity rover to land at the right spot on Mars, it's like firing an arrow out of a bow while you are on a moving car, like on the freeway, trying to hit a target on another car that's in New York City, and if you're in San Francisco on one car and the other car's in New York City, okay, and you're firing an arrow, and you're trying to hit an object that is the size of Lincoln's eye on a penny. Oh, and it's a little bit of a cheat, because not only do you get to launch the arrow, but at 3 times on the way that the arrow gets to New York, you can kind of grab it and correct its, right? They hit a 100 meter by 100 meter patch of the Martian atmosphere from Earth. That's how accurate they were when they hit. It's like the only way you can pull that off is to have a correct understanding of what's actually going on with these orbits. And Kepler's laws are what they use to do it. Of course, they use supercomputers to track all of the variables and do all those kinds of things. But we still do all of our planetary mechanics with Kepler's laws. It's pretty darned amazing. The Kepler's laws that you see right here are the ones for perfect circles, by the way. This one I drew in the box assumes a circular orbit. So all of our stuff from circles still applies, right? Just to review, right? Like the period and velocity and radius of a circle, right? All still apply right there. So just keep that in mind as we go through it. All right, let's do it. Let me show you like working with Kepler's laws, just as an example of how to work through a problem where Kepler's laws are involved. Again, the first two are conceptual in nature, elliptical orbits. And now you know, where do planets move the fastest in their elliptical orbits? Closest to the... by the way, I don't have time for this, but we're going to talk about it anyway because I don't want anybody leaving my class without understanding why the seasons happen. When in the calendar year is Earth closest to the sun? It is not the summer. In fact, the summer is when we are furthest from the sun in our orbit. Our closest approach happens January-ish. Sometimes the tail end of December, sometimes the very end of January. It wobbles around a little bit. But by and large, when we are experiencing our winter in the northern hemisphere, that is when we are at the closest point to the sun in our orbit. So why is summer so hot? If we're further from the sun in the summertime, why is it so darn hot? Because seasons have nothing to do with how far away from the sun we are. Seasons have everything to do with our rotational axis, our 24-day rotational cycle, 24-hour rotational cycle, being tilted with respect to our orbital plane. This tilt of Earth's axis with respect to the direction it's orbiting is the reason for the seasons. And the reason we call summer so hot is because that's the point in our orbit when our hemisphere is more directly pointed at the sun. The sun's strength really doesn't alter in our mostly circular orbit. Yes, we get closer. Yes, we get further away. But a couple million miles actually isn't going to change the power output of the sun. Instead, it's how directly those sun's rays hit us. In the summertime, in the northern hemisphere, the sun is like almost directly above, beating straight down on us. In the wintertime, people will say that the sun feels weaker, right? It's actually not. It's gotten lower in the sky from our point of view, but basically in our winter, our axis, our northern hemisphere is pointed away from the sun, and the sun's light hits the surface of the planet more obliquely. It gets spread out over more area. You can do this trick with your phone's camera, okay? I don't know if you can see, if I hold my camera, my flashlight, right? And do you see how there's almost a nice circular flashlight on the board right there? But if I tilt it, what happens to the brightness of the dot? See how the brightness goes down? And I've spread the same amount of energy over a bigger area. That's what's happening in the wintertime for us. Summertime, we're getting the direct sunlight, but in the wintertime, because of the tilt of our axis, it gets spread out. Okay? Same amount of energy. Didn't change the native brightness of the light. I just changed how much area I was spreading it out over. So our seasons are not determined by how close we are to the sun. They are determined by the tilt of our axis. So anyway, that was a little bit of a side note. This is a picture of Alpha and Beta Centauri, okay? In the Alpha Centauri system, there is a star called Proxima Centauri. It's called Proxima Centauri because it is the star that is closest to our own star. Our sun, called the sun, is our closest star to our planet but this is the next closest star. It lies at about 4.1 light years away. In other words, a radio signal from us to Proxima Centauri takes about 4 years to get there. And if anybody's listening and wants to send us their TikToks, it takes 4 years to get back. Okay? Nobody's listening. Or at least they haven't admitted to listening, which I'm not surprised if you've seen any part of TikTok. All right. So let's say that we are in our starship and we go to Proxima Centauri b. Okay? And we are in orbit around this planet. And we pull up some information. We measure our orbital period, right, of 1.57 Earth hours. I don't know what other hours we do it in because we're Earthlings. And so that's what we're going to do. All right. They gave us somehow, this is interesting, somehow our spaceship's able to tell us the total distance between the core and our ship, but isn't able to tell us what the mass of the planet is. This is kind of interesting. All right. So that distance that they gave us here, that's the radius of the orbit, right? Like I said that radius is center to center. One of the tricks that textbooks love to pull on you is tell you the orbital altitude of something. They'll say the planets, for example, let's just get a planet down here. And by the way, all of my satellites look like TIE fighters. I don't know why. Okay? And let's say you got going around there, right? They'll say the planet's radius is 1,000 kilometers and the orbital altitude is 200 kilometers. What's the radius of the orbit? It's 1,200. So watch out for that word altitude. Okay? Altitude is always measured from the surface, whereas the orbital radius is always measured from the center. So just, again, watch out. Okay. So we know our orbital radius is 7,500 kilometers. There's that altitude word. I just warned you about it. Okay? 500 kilometers. So let's update our picture here. So the whole enchilada is 7,500, but this distance right here is just 500, right? So what's like the distance to the surface? 7,000. It's 7,000 from the center, right? Okay. There we go. They want to know the mass of Proxima Centauri b. All right. First problem that even if you have no idea how to do orbital mechanics, you're totally lost about Kepler's law. There's something right now that should be bothering you. Yeah, it's the hours and kilometers, right? What do we need to do with these? We need to get them into seconds and meters. You get to standard units. If you don't do standard units, it's not going to work because big G is going to assume standard units. So 1.57 hours. And for every 1 hour, there are 3,600 seconds, right? So let's see. Did I get this one? 56. I got 5,667.
1.57 times 3,600.
Yeah.
I got 5,652.
All right. We'll go with your number because I don't trust me. All right. And then how do I write 7,500 kilometers in meters? Well, I just literally, instead of K, what do I write? 7,500 times 10 to the 3. Quick conversion. Change the K into a times 10 to the 3 and you're good to go. Okay, we got that. Okay, so how are we going to find the mass? Well, we got an equation. It's a horrible one, but it's ours. 2 pi r to the 3 halves all over square root of big G times big M. Oh, I never talked about what big M is. Big M is the mass of the thing that's being orbited, not the orbiting thing. The orbiting thing doesn't matter. Mass of our spaceship doesn't matter. Mass of a moon doesn't matter. What matters is the mass of the thing being orbited. So if you are in orbit around the Earth, what mass do you put in here? Earth. If you're in orbit around the sun, what mass do you put in here? If you're in orbit around the moon, what mass do you put in here? Got the idea? Okay. All right, so we're going to find the mass of the planet by solving for the mass. How do I get the mass out of this thing? Okay, get ChatGPT to do it, sure. Can I square both sides? I gotta get the thing out of the square root, right? So I'm gonna attack the square root first. So if I square both sides, oh my gosh, that's t squared equals, what is that, a 4 pi, oh, this gets better, r cubed, right? Because the 2 and the 1/2, and right, they cancel. All over big, oh, this isn't so bad. And then I do some swapperoos. So this is going to be 4 pi squared r cubed all over big G t squared. I divided both sides by t squared, and I multiplied both sides by m. There you go. That's what I did. So now I can go. And as a matter of fact, you could probably just put that like in your toolbox so that you don't have to keep solving it over and over again, right? Kepler's third law solved for mass. All right, so now we can just chuck stuff in, right? 4 pi squared, my r, 7,500 times 10 to the 3. And I got to cube that. Good luck in your calculator with that. 6.67 times 10 to the minus 11. And then 5,652 seconds squared. All of those are in SI units. I'm solving for a mass. So what should it come out in? What unit? Kilograms. 7.77 times 10 to the 24 kilograms. By way of comparison, the Earth is 5.6? I don't remember anymore. 5.67 times 10 to the 24 kilograms?
5.98.
98. There was numbers in it. I knew that. So which of these planets, us or Proxima Centauri b, has more mass? Proxima Centauri b, but not by much, right? Not by much. So very similar in mass. Now what do they ask us to do? So that we found the mass. Okay, if an object weighs that much on Earth, what would its weight be on Proxima Centauri b? Okay, and by the way, Proxima Centauri b is a real place. I picked up the planetary data from Wikipedia, which got it from NASA. So using, ironically, maybe not ironically, the Kepler Space Telescope. So what's the thing that stays the same? No matter where we go in the universe. Not weight. It is, okay, that was a loaded question. Yes, the gravitational constant stays the same. Mass is what I was searching for. When we calculate weight, it's little m times little g. But the thing that stays the same no matter where we are is mass. Is little g different on Proxima Centauri b? Yes, because we know that little g, part B by the way, little g, we already figured this out. It was big G times the mass of the planet divided by r squared. So, how are we going to find the weight of an object on the surface of Proxima Centauri b? Remember, weight is equal to m times g. So if we can find little g for the surface of Proxima Centauri b, which we can now, right? Because we've got big G, we've got the mass of the planet, and we know the distance to the surface of the planet from its center, right? We can find little g on Proxima Centauri b. I went and I threw in the numbers. I got 10.6 meters per second squared. So, does gravity feel weaker or stronger on the surface of Proxima Centauri b? Little bit stronger, but not by much. And in fact, after a couple hours of just being on the surface of Proxima, you probably wouldn't notice any difference. Initially you might, but after just a little bit, you probably wouldn't notice the extra 1 meter per second squared. All right. But now we need to know the mass. How are we going to find the mass? We know the weight on Earth, right? So if we use Earth's, right? If we divide by 9.8, we did this yesterday, that gets us the mass. The mass I found was not something I wrote down. 57.1 kilograms. I did write it down, but I can't read my own handwriting. And then now that we know the mass, and the mass is the same everywhere, to find the weight on Proxima Centauri b, I just take that mass, 57.1, times 10.6 now, and that gets me 604 newtons. Yeah, I'll just probably round off there. Okay. So we can do all kinds of orbital mechanics. We can do planetary mechanics, all kinds of stuff, just working from Kepler's laws. This homework isn't due until next Wednesday, right? Did I get that right?
Yes.
That's a good thing because I'm not quite done with chapter. I seem to be just about 10 minutes behind. all semester long, I've been about 10 minutes behind. So I will finish up very quickly on Tuesday with the last little bits. We got to do escape velocity with chapter 5. And then we'll get started on chapter 6, which is, chapter 6 is where we're going to start energy. And it is a bit of a different animal. So be ready. And if I don't see you in GRASP, have a great weekend.